Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will learn about a very important type of map from one group to another called a homomorphism. So this is the definition of a homomorphism. So it's a map from two groups G and H. So remember, a set of elements has to form a group under an operation. So we're letting the operation be a star in group G and circle in group H. So X and Y are members of G. So the map phi is a homomorphism if it maps from G to H. It is a function and it satisfies this definition here. This is the important part of the definition. So what this is saying is it doesn't matter whether we combine X and Y by the operation first and then map it, or we map each separately and then combine them. So let's look at a little picture to illustrate this. So let's say we have our two elements here, X and Y. So phi is a map. It will take X to some element here in H. So that's what we call phi of X. So note that phi of X is an element in H. And this map, because it's a function, it will map everything in G. So it will also map Y, and it will go to some other element in H. They may be the same, they may not be. This will call phi of Y. So, because G is a group, if we first combine X and Y before mapping them, if we combine them under the operation star, we will get another member of G, because G must be closed under this operation because it's a group. And similarly, phi X and phi of Y, they are elements of H, so we can combine them in H to get another element of H. So we'll pick that element there. So what a homomorphism is saying is that it doesn't matter if I combine these two to get this first, then I map by phi. That gives me the same answer. I end up in the same place as if I map X, then map Y, then combine them in the second group under the operation. I end up at the exact same place. So it doesn't matter whether you perform the operation first or the map first. So homomorphisms are sort of a measurement about how structurally similar two groups are. So if there is a non-trivial homomorphism, because every two groups will have at least one homomorphism between them, the trivial homomorphism, which maps every element to the identity. But if there's a non-trivial homomorphism, it says that the groups are sort of structurally similar. It doesn't say that they're the same, but they're sort of structurally similar in the sense that, you know, equations that are true in the first group will be true in the second group. So this is a measure about how structurally similar two groups are. So let's look at an example that you would know. So an example you know is reduction a modulo. So this works for any modulo. I'm just choosing 5. So if I take an integer and I reduce it modulo 5, that's a map from the integers, remember that includes positive and negative integers, to the integers modulo 5. So note, remember these are both groups. Z, the set of integers, is an abelian group under addition. So too is Z5, the integers modulo 5. They form an abelian group under addition. So this is a map from one group to another. Now this is a function because every integer, everything in the first group, can get mapped by reduction modulo 5. Any integer can be reduced modulo 5. There's no integer that doesn't get reduced modulo 5. So this is a function. So to show that it's a homomorphism, we need to include the operation. So as I said, both of these are groups under addition. So this map phi turns out to be a homomorphism using the operation addition because it doesn't matter whether you take two integers and add them, then reduce modulo 5. Or if you reduce each integer modulo 5, then add them, you will get the same number. So for example, let's say I wanted to add 12 and 23. Okay, so I can add them first and get 35, and then reduce modulo 5. So 35 is 0 mod 5. I will get the same answer as if I first reduce them. So 12 is equivalent to 2 modulo 5. 23 is equivalent to 3 modulo 5. So that's equivalent to 2 plus 3, which is 5, which is equivalent to 0 mod 5. So I get the same answer whether I add the integers then reduce modulo 5 or reduce modulo 5 and then add. That's why phi is a homomorphism. So on the next slide, I'm just going to quickly prove that it's a homomorphism. So let's say I have any two integers a and b, and we're going to look at what happens to the modulo 5. So note, for any integer, I can write it as 5 times another integer plus an integer. So for example, if I had 31, I can write it as 6 times 5, something times 5 plus another integer. If I have, say, minus 42, I can write it as negative 9 times 5, something times 5 plus an integer. Note that these integers here, so m and n, always going to be less than 5, 0, 1, 2, 3, or 4, okay? So, what happens when I add them first? So, a plus b, what will I get? Well, I will get 5x plus 5y plus m plus n. I can change the order because addition is commutative. So if I add them together and reduce modulo 5, this will be 0 mod 5 because it's a multiple of 5. This will be 0 mod 5 because it's a multiple of 5. So I'm just left with m plus n mod 5. Okay? So what I've done here is I've added them up and then reduced. So I've added them first and then I've mapped them according to phi. So what if I first reduce a modulo 5? So then I would just get 5x plus m would just reduce to m mod 5. And similarly, phi of b, so I'm going to reduce this modulo 5. So that will just be n modulo 5. If I then combine them, I get phi a plus phi of b equals m plus n in modulo 5. They are equivalent. So I got the same answer if I added them, then reduced modulo 5, as if I reduced modulo 5, then added them. So what I've shown here is that phi of a plus b is the same as phi of a plus phi of b. So I've shown that phi is a homomorphism. Because I used arbitrary integers x, y, m, and n, they could be any integer. I've shown that it works for all integers. So phi is a homomorphic map. So I just want you to be aware this map is clearly not one-to-one or injective, because it will map more than one integer in Z to the same integer in Z5. So for example, this will map 5 will be mapped by phi to 0, but 10 will be mapped to 0. Similarly, 300 will get mapped by phi to 0. So you can see it will map different elements in the first group to the same element in the second group. So this map is not one-to-one. So note 0 is the identity because we're talking about addition. So there is a special name for all the elements that get mapped to the identity. That is called the kernel. So the kernel is the set of all elements of G, the first group, that are mapped to IH means the identity in H. So in this case, G, the first group, was the set of all integers under addition. So the kernel of the map phi, which reduced an integer modulo 5, so the kernel would be all multiples of 5 because they are the elements that get reduced to 0, the identity in H. H, of course, in this case, was the group 0, 1, 2, 3, 4, the integers modulo 5, okay? So the kernel is the set of all elements in the first group that are mapped to the identity in the second group by phi, which is the homomorphism, all right? So I just want to make a few quick notes about isomorphisms and property of homomorphisms. So, if we have a homomorphism phi, and it's mapping from group G to group H, if that map is also bijective, we say the map is an isomorphism. And if there is an isomorphism between two groups, we say the groups are isomorphic. That means they have the exact same structure. They're pretty much the same group written in a different way. So now I'm going to give you an example of an isomorphism. So let's look at these two groups here. So G is the cyclic group with 6 elements. It also follows the rule C to the power of 6 is equal to 1 and follows the usual index laws. And H is the set of integers modulo 6, where 6 is equivalent to 0. So note G is a group under multiplication and H under addition. Even though these two groups are groups under different operations, they can still be isomorphic. So to show that they're isomorphic, I have to show that there is a map between them that is an isomorphism. So I've got to define a map. So I'm going to define the map phi, which goes from G to H. And what it's going to do is it's going to take the element C to the power of K in G and map it to K in H. It's just going to map each element in G to whatever its power is in H. So note, C to the power of 0 is equal to 1. That's just the index law. So it's going to map, this map phi is going to map 1 to 0, C to the power of 0 to 0, C to the power of 1 to 1, C to the power of 2 gets mapped to 2, and so on. So this map is clearly bijective because each member of G is paired with one and only one member of H. Each member of H is paired with one and only one member of G. In other words, each member of G gets mapped to a different element of H, and there are no elements of H that have not been mapped to. So this is clearly a bijective map. I haven't shown that these two groups are isomorphic yet. I have to show that this bijective map is also a homomorphism. What I want to do is I want to show that phi of A times B is equal to phi of A plus phi of B. So here I'm using A and B as arbitrary elements of the first group. So here I have a times because if I'm combining A and B together in G, their group operation is times. But here I need to use a plus because phi A is in H, phi B is in H. So this is occurring in H, this is occurring in G, which is why there are different operations. So let's say that A is the element in G that has C to the power of K. I can write any element in G as C to the power of something because, as I said before, 1 is C to the power of 0. So let's let B be C to the power of L. So phi of A times B is just going to be phi of C to the power of K times C to the power of L. But that just equals C to the power of K plus L. So what the map does is it takes the power of C and it maps to that element in H. So in H, that will just be mapped to K plus L. So let's look at the right-hand side of the equation. So phi of A, if A is C to the power of K, that will just get mapped to K. So phi of B, that will just map c to the power of L to L. So phi of A plus phi of B is just going to be K plus L. So note these are the same. It satisfies the definition of a homomorphism. Phi of A times B is equal to phi of A plus phi of B. Therefore, the map phi is a homomorphism. Because it was also bijective, phi is an isomorphism, and therefore G and H are isomorphic. And that sort of makes sense. What we're saying here, 0 in H does essentially the same thing as 1 does in G. They're both identities. 0 is the identity under addition, because the group operation's addition. 1 is the identity under multiplication. If you look at these two elements, C to the power of 3 and 3, they essentially do the same thing. In both cases, they are its own inverse. 3 plus 3 gives you 0 in H. C to the power of 3 times C to the power of 3 gives you 1 in G. This element and this element, they essentially do the same thing. I need to times this one by this one to get the identity. Whereas in H, I add this one and this one to get the identity. So that's what we mean by isomorphic. They're pretty much the same group, just written with different notation. So there is an isomorphism between G and H, therefore they are isomorphic, and we usually write it like this. G is congruent to H. They're essentially the same group. All right, let's just look at one more thing, and that is some important properties of homomorphisms. So I said before that homomorphisms are sort of a measure of how structurally similar groups are. There's two important properties of homomorphisms that allow that to happen. So the first is that homomorphisms map the identity of one group to the identity of another group, and they also map inverses to inverses. So I'm actually going to prove the first of those, and the second one will be left to you to prove as an exercise. So if I have my map here, phi from G to H, so again G and H are groups, this means that phi is a homomorphism. So what I'm going to propose, the proposition will be that phi, which is a homomorphism, maps the identity of the first group to the identity of the second group. So we're going to go ahead and prove this. So as we saw in the last example, two groups can have an identity that is different. So in the previous slide, we saw G had the identity 1 because it was a group under multiplication, and H had the identity 0 because it was a group under addition. So we're going to let IG be the identity in group G. And of course, we're going to let IH be the identity in H. So what we want to do is we want to prove that if I take my map phi and apply it to the identity in G, it will just give me the identity in H. And I'm going to use this property up here. So what we're going to do is we are going to apply phi, the map, to the identity in G, operated on the identity G with itself. Okay? So, because of the properties of a homomorphism, that will be phi operated on the identity, and then we operate that in H with itself. So that's what we have here. But of course, the identity operated on itself in G is just the identity. So that will just be IG. So I have this equation now. But the important things to know is that we're now in H. This is an element in H, this is an element in H, and this is an element in H. Because what we've done is we've started with the identity in G, and we've mapped it via phi to some element in H. And we're proving that that element is the identity. So we're now in H. Now, because H is a group, each element has an inverse. So what we can do is we can multiply each side of this equation by 5i of g, whatever that is, we can multiply by its inverse. So we can multiply by the inverse of this element. It will be somewhere in the group by the definition of a group. So if we times one side by the inverse, we have to times the other side by the inverse. So of course, inverses cancel each other out. So these will cancel each other out, and this here, the element times its inverse. The element multiplied by its inverse in H will give you the identity in H. So I have IH, the identity in H on the left-hand side, is equal to phi of IG. And that is what I wanted to show. I wanted to show that if I apply phi to the identity in G, it will give me the identity in H. So that was actually a pretty simple proof. So note also, homomorphisms map inverses to inverses, but I've left that proof as an exercise. Alright, I'm sorry for the long video. Hope you found it informative. This has been the luckiest maths teacher in the world. Have a great day.